When measuring signals, even if the wiring and instrument adjustments are correct, the waveform on the screen may still appear distorted. This issue could be due to selecting the wrong oscilloscope bandwidth. The bandwidth of an oscilloscope is the most critical performance metric. Today, we'll break down the core logic of oscilloscope bandwidth from the perspectives of frequency and wavelength. Let's start with the frequency we most frequently encounter, and first understand the official definition of bandwidth. When imparting a sine wave signal, the oscilloscope measures the signal amplitude to attenuate to 0.707 times the true value, the corresponding highest frequency. Here is a key point. The signals we actually measure, such as square waves and pulses, are not single-frequency sine waves but are instead composed of a fundamental wave combined with numerous higher harmonics. If the oscilloscope bandwidth is sufficient, these higher harmonics can be fully captured, resulting in steep edges and square waveforms. However, if the bandwidth is insufficient, higher harmonics will be directly filtered out, causing the edges to slow down and round at the top, leading to distortion. This is why high-bandwidth oscilloscopes must be chosen for measuring high-speed signals. So from a frequency perspective, bandwidth determines how many fast signals you can detect, with faster signals requiring higher bandwidth. From the perspective of wavelength, let's look at bandwidth. The electrical signals we measure, when propagating through probes and cables, are actually electromagnetic waves. The propagation speed is close to the speed of light. Wavelength equals the speed of wave propagation divided by frequency. The higher the frequency, the shorter the wavelength, and the richer the high-frequency details in the signal. The bandwidth of an oscilloscope is essentially the shortest wavelength or highest frequency component it can distinguish and capture. The higher the frequency and shorter the wavelength of the signal, the higher the bandwidth requirement for the oscilloscope. 100 MHz bandwidth can only capture signals with lower frequencies and longer wavelengths. To see high-speed signals with short wavelengths such as 1 GHz and 10 GHz clearly, higher bandwidth is necessary. In summary, in terms of frequency, bandwidth is the frequency admission upper limit of a signal, which determines whether high-speed signals can be measured. From the perspective of wavelength, bandwidth is the shortest wavelength that can be captured. The shorter the wavelength, the higher the frequency, and the higher the required bandwidth.